Welcome everyone. So, this course introduces the algebraic structures through some examples coming from combinatorics, number theory, graph theory and so on. So, let us actually first begin with asking this question, what is mathematics? So, mathematics has been around in human history for a long time. So, the oldest and least disputed historical evidence of ancient mathematics is from Babylon, roughly from 1800 BC. Since then, mathematics has progressed to become a vast edifice encompassing several areas that can be broadly classified as analysis, algebra, geometry and discrete mathematics. Of course, there are significant overlaps between these categories. At a high level, what is analysis? Analysis is the study of inequalities and approximation. What is algebra? Algebra is the study of equalities. Similarly, geometry is the study of space and structures, and discrete mathematics that studies logic, step by step procedures, computations and counting problems coming from combinatorics. Okay, now let us actually talk about what is algebra. So, algebra concerns itself with noticing patterns in proofs of various kinds and abstracting out the essential features into definitions of some algebraic structures. So, these algebraic structures, for example, we will be seeing like groups, rings, fields and so on in this course. So, these algebraic structures are then studied in their own right. So, you define what is called group by looking at various examples that comes from various different places like geometry, number theory, combinatorics and so on, and then you unify these algebraic structures and put them into axioms and call them groups, and then you study them on their own right. Okay, here are some concrete examples in the form of questions that can be addressed using algebra. So, the very first question that comes from this solving polynomial equations. So, one can ask, is there a formula like the quadratic formula that you must have seen in schools, which actually solves the quadratic polynomial by radicals, and similar formulas whether it is available for higher degree polynomials. So, that one can ask. So, why is it unreasonable to expect such a formula for degree greater than or equal to 5? So, that kind of question that one can ask. So, one can do some basic calculation and then see. So, similar formulas can be obtained for degree 3, but if you use little bit more energy and time, you can also actually come up with similar formula for degree 4. But beyond that, it is indeed an important and the main theorem of Galois theory that says that degree polynomials of degree greater than or equal to 5, so that cannot be solved by radicals. So, those kind of questions one can ask using algebra by unifying. So, what is going behind in all those algebraic objects. Okay. So, now like how one can actually go from this type of question to some questions about combinatorics. So, we can also ask this question like we want to devise a walk through the city of Königsberg that crosses each of its bridges exactly once. Even though this looks like some real life problem, one can use graph theory to solve this problem. And here is another question about numbers. So, we want to find an integer x such that it leaves a remainder a1 when divided by n1 and leaves remainder a2 when divided by n2 and so on. And such questions will be addressed in basic number theory chapter. Here is another question that involves polynomials. So, we can ask whether one can express the following polynomial like x 1 cube plus etcetera x 100 power 3 in terms of the what so called elementary symmetric polynomials, which are defined as x 1 plus etcetera x 100 and then sum of this product x I x j and then sum of product x I x j x k. And there is another question that also like I want to say, like these questions actually involve questions coming from algebra, but one can also look at the application side. So, we can also ask how does one secure information when it is transmitted over the internet. So, this is what actually addressed in coding theory and cryptography, and lots of algebra will be used in addressing these type of questions. So, for example, higher field theory and then group theory and so on. So, they will be used in answering these type of questions. So, one can wonder about what is at the bottom of mathematics. So, usually mathematicians pride on being rigorous and keepers of absolute truth. However, one needs some real world element to even start talking about mathematics, either a human or a computer plugged into a socket. So, what lies at the interface of the real world and mathematics? In other words, where must we begin? So, we have to begin somewhere. So, where to begin? So, that is the question. So, in high school one is often tortured with the basics of set theory, including Venn diagrams and so on. But then if you think about it, sets are just defined in high school as collections of things or objects or elements. However, sets were amorphously defined to be the collections of things, objects or elements. It is true that the interface of the real world and mathematics is not amorphous, but unfortunately such a naive view of sets is not good enough to be a foundation for mathematics. So, one has to be rigorous. So, that is what as mathematician we like. So, we have to make everything very rigorous. So, defining like collection of some things satisfying some properties, that is not good enough. So, sometimes that will lead to some ambiguity. So, we want to avoid such ambiguities. Okay. Indeed, the British philosopher and mathematician Bertrand Russel discovered a paradox in naive set theory. So, the paradox is usually stated as follows. So, if there is a barber in London who saves all those and only those who do not save themselves, then who saves the barber? So, if you think about it, so barber cannot shave himself, and if he does not shave himself, then he forced to shave himself, because the barber actually shaves all those and only those who do not shave themselves. So, this actually leads to paradox. So, this is actually the only resolution of such a paradox is that such a barber does not exist. In the language of naive set theory, the same paradox can be formulated by considering the set that consisting of all sets that do not contain themselves as elements. And if you think about it, we will actually rigorously prove this in later part of the course that such a set cannot exist. So, the point, what is the point? The point is that not everything that you define using plain English, so that should be considered as a set. Okay. So, for example, the one that we defined consisting of all sets that do not contain themselves as subsets, So, that sounds like a well defined set, but it is indeed not a set. Okay. So, that is what something that we want to convince ourselves in this course. So, in other words, we need to have axioms that tells how to construct sets from standard or God given sets. Okay. Of course, we have to start with some scratch. Okay. The best place to start with is what is called sunyam, which is empty. So, you start with empty set, that you take it as God given set, and then from that rest of the things you want to construct. So, that is the ultimate goal of this course. So, one might rightly have the following objection. What is the objection? If one wants to axiomatize set theory itself, then one would have to use phrases like for all sets that do something, there exists something else. So, however, the phrases for all and there exists are themselves part of logic. So, then this leads to the following question: should we axiomatize logic itself? If so, in terms of what? Do we not have a danger of circularity? We of course do this, but can we at least clearly demarcate the interface between the real world and mathematics? So, we do not want to get into some circular arguments. Okay. So, we want to make things very clear. So, that is what we want to actually do this in this course. So, the way out is the following. So, we are assumed to be able to write finite strings from a finite alphabet consisting of certain symbols, whilst following some rules that include the axioms of logic. So, what we means here, we as humans or computers or some intelligent aliens. Okay. So, the capabilities assumed are pattern matching and substitution into formulas. So, this is all we have. The symbols in the alphabet include this for all, there exist, parentheses, commas and so on. So, the logical connectivities like and, or, not, those things also should be used. And like I said, we take this empty set, that is like God given set as from to begin with, and of course, the binary relationship like equality, belongs to. So, these should be again used, an infinite collection of variables x 1 etc., they also should be used as symbols. Okay. So, these symbols, so they are all like, let us assume that we understand them. So, there are two kinds of strings one can write. The first one is terms. So, terms, that means variables, constants and more generally things that do not have a truth value. And the second kind of strings one can write, they are formulas, things that have a truth value. So, the terms, the variables, for example, x 1, it does not have any truth value, but then if we say that a plus b whole square equal to a square plus b square plus 2ab, that has a truth value, because it is true for all a b real numbers, for example. So, there are two kinds of strings, like I said, first one is terms, have no truth value, second one is formulas that have truth value. So, there are some rules of deductions like P implies Q that allow us to come up with new formulas from old ones. So, we start deriving some formulas which are the truth values checked, and using those formulas one can come up with new formulas, and that is where these deductions or implications are derived. We need some formulae to begin with in order to find new ones. So, that is the basic ideas. These formulae are templates for writing formulae are obtained from the axioms of set theory. So, we develop the set theory, the foundation. From set theory we will do everything else. So, equipped with these axioms, one can write every mathematical theorem as a formula in the language. In other words, the capabilities of computer language like C++ is enough to do mathematics. So, one can write all the axioms of set theory and logic itself as a program in C++. One can connect the abstraction to real life by executing such a program. So, rather than going in the completely formal route which can be found in several textbooks, what we do in this course, we shall simply present the axioms of set theory in more intuitive logic. So, that is what we are going to do now. So, the axioms are called Zermelo-Fraenkel axioms, simply denoted as ZF axioms, in honor of Ernst Zermelo and Abraham Fraenkel. And there is another important axiom called the axiom of choice that many mathematicians are comfortable with. That means they are comfortable in using and so on, and hence one wants to include that in the axiom of set theory. And including that axiom, the full list of axioms will be denoted as ZFC, Zermelo-Fraenkel with the choice. Okay. So, what are the ZF axioms of set theory? All objects in mathematics are sets. Okay, that is the first punchline. So, that means what? That means whatever you see in mathematics like numbers or equations, okay, not the equations, the numbers or any objects that you are actually going to work with, for example, functions, relations, groups, rings, all of them are sets. Okay. Even functions are sets. So, that is the interpretation that one should be comfortable with. So, in other words, the elements of sets are sets in self. So, sometimes you write like for example, natural number as 1, 2, 3 etc., but the elements 1, 2, 3 all of them one can interpret as sets. So, that is how we can think of all objects that are represented in mathematics are sets. So, we will actually rigorously do this in later part of the course. So, we read x belongs to A as x belongs to A or x is an element of A. So, given two sets A and B, it is meaningful to ask whether A belongs to B or not, because both of them are sets, and since elements can be sets, so then we can ask whether A belongs to B or not. So, that is a very valid question. The ZF axioms are as follows. So, they formalizes the sets. Okay. So, one begins with the very first axioms called extensionality. So, that talks about when two sets are equal. So, you call two sets are equal if they have same set of elements. So, in more logical terms, you write it as for x and capital A and capital B, we have A equal to B if and only if whenever x is in A, that should imply x is in B and vice versa. That means, x belongs to A if and only if x belongs to B. So, that is how you read this. So, this means x belongs to capital A if and only if x belongs to capital B. And this is the way actually we call, or we say that two sets are equal. So, now what is the second axiom? The second axiom is about existence of empty set, and since we can't prove the existence of empty set, we keep that as part of the axioms. So, what does it mean? It means you declare that there is a set that contains no elements. And if you think about it, the uniqueness of such a set follows from the axiom of extensionality. So, you prove that two sets are equal if they actually have same set of elements. And now, if you start with two sets that contains no elements, then using extensionality you can easily prove that they must be same. So, this unique set is called the null set or the empty set, and it is usually denoted by this simple empty set. Okay. You draw this oval shape and then put cross across this. This is what we write it as empty set. And once we know empty set, we can call, when capital A given set is non-empty, you call the set is non-empty if A is different from empty set. We already understood when two sets are equal. So, that actually immediately tells that when two sets are not equal by contrapositive. So, then one can actually easily see that from using logic. So, A is non-empty means there exists an element inside A. So, you can take it as exercise and then think about it. If you start with a non-empty set, then one can prove that there exists an element x inside that set. What is the third axiom? The third axiom talks about regularity. So, the regularity tells about, given a non-empty set A and then an element inside that set A, then what is the relationship between those two sets? Okay. For example, I can take a set 1, 2 and then element 1. So, since the element 1 itself can be thought of as a set, so what can you say about these two different sets, which is the set 1, 2 and the set 1, and we do not want them to have any ambiguous between them. So, we expect them to be disjoint. Okay. So, what is the meaning of disjoint? Disjoint means, so there are no common elements between those two sets. Okay. So, that is again like we add it in the axiom. So, every non-empty set A contains an element x such that x and A, they are disjoint sets. Okay. So, this is something very important, and we will see that later, like this will be used. So, the fourth axiom that talks about pairing, and what it is, if A and B are sets, then there exists a set which contains A and B as elements. Okay. If you think about it, so basically we are saying that, so given sets A and B, what you can do? You can consider this new set consisting of elements capital A and B, and that is indeed part of some set C. So, there exists set C such that capital A and capital B becomes elements of this new set capital C. Okay. So, you can take it as exercise and then prove that given two A and B sets, there exists a unique set that contains A and B as only elements, and which is usually denoted by this set consisting of A B. Now, we can define what is subset. A subset B is, so we call a set B a subset of a set capital A if every element of B is also an element of capital A. So, in this case we just write B is subset of A. So, if you want to use logic, so for all x in B we have x in capital A. Okay. For each element of B we must have that element is an element of capital A. In that case you write B is subset of A. Now, we have this fifth axiom called subset schema. This axiom is actually a template for several axioms. So, this is somewhat very important axiom. So, this axiom tells about how to construct sets. Basically, this axiom actually justifies the popular set builder notation that is used in order to define sets. So, basically what it says, if a set capital A given and P is a formula describing a property, so then you collect the elements x from capital A satisfying the property P. So, that means you collect x in capital A such that P of x holds, and we demand that that is again a set. So, this formula could be any formula. For example, it could be given by some algebraic formulas, or it can be given by some inequalities that appearing in analysis. So, it can be given by using some complicated functions like trigonometric functions or exponential functions or logarithmic functions and so on. So, various formulas that one can actually write it down in practice, but this subset schema guarantees that if A is a set and P is a formula that describes property, so then you collect those elements x in A satisfying that property. So, that should be again a set. Like I said, this axiom justifies the popular set builder notation that is used in practice, and it is crucial to restrict ourselves to constructing subsets of existing sets using the set builder method. So, otherwise what happens? So, we get paradox like Russel paradox that starts appearing. So, indeed, so let us look at this exercise. So, you collect this set of all sets, okay. You take set of all sets x such that x is a set and x doesn't belongs to x. So, one can actually collect such a set. Now, one can ask whether this capital X is a set or not. If you think about it, this capital X cannot be a set. So, this actually tells you that the set of all set cannot be a set. Why this is not a set? Okay. So, let us go through the argument. So, suppose X is a set. So, then since X is being a set, so one can ask whether X belongs to the collection capital X. Okay. So, we should be able to decide whether given element is part of the set or not. Okay. So, now that means either we will have x is part of x or x is not part of x. Okay, I am talking about this capital X. So, this capital X which is defined using this thing x equal to those x such that x is a set and x is not element of x, and we are asking whether this capital X is again part of this collection or not. So, if you think about it, both will give you contradiction, because if x is inside capital X, that would imply that using the property that is defined for this to define the collection capital X, that would imply that capital X does not belong to capital X using this property. Okay. So, this leads to a contradiction. And similarly, if x does not belongs to x, again using the property that defines capital X, you can see that x is part of capital X, again you get a contradiction. So, in either case x is in x or x is not in x, we arrive a contradiction. So, that tells you that capital X cannot be a set. So, this assumption is wrong. So, if you do not want to run into such paradox, so one should not use constructing subsets of existing sets using the set builder method. Okay. So, that is the punchline. So, now I will actually give some exercises. So, you take A and B to be two sets and then prove existence and uniqueness of the intersection A intersection B and difference A difference B. So, the only axioms up to this axiom 1 to 5 that you can use to prove this. Okay. So, that is something I am leaving it you to. So, now what is the sixth axiom? The sixth axiom actually guarantees that given a set, there exists always a power set of that set. What is the power set? So, that is a set that contains all subsets of capital A, and it is usually denoted by P of A. So, P of A is nothing but, so it collects all possible subsets of capital A. Since we cannot prove power set exists, so we actually add that into the axiom. Similarly, we actually tell you that union is also exist. Since we will be talking about union over like any collection, so the collection need not be finite. So, we will be just put this as axiom. So, what this axiom 7 says? It is about union. If A is a set of sets, that means it is a collection of sets, then there exists a set called union A that contains every element that belongs to some element of capital A. So, in practice the way we write, so this A is collection of sets, usually it is indexed over some, let us say capital lambda. I will be actually talking about the indexing set and so on later, but in practice this is how one writes the union. The union A is exactly the union of A alpha, alpha in capital lambda, and the axiom 7 guarantees that such union exists. So, indeed one can use the axiom 1 to 5 in order to prove the existence of A union B. Maybe you can take that as exercise. For the arbitrary union, so we will use this axiom, and existence of finite union also there. Okay. So, the axiom 8 that talks about replacement. So, it ensures that the image of a set under a definable function is again a set. So, the definable function like there are various functions that you will be seeing, for example, like something like uses algebraic formulas or some analytic formulas and so on. And what the replacement axiom says, it talks about like more precisely, if for every x in A there exists a unique y such that P of x y holds, where P of x y is the property which is given by like algebraic formulas or analytic formulas and so on. So, then there exists a set which is collection of y such that P of x y holds for some x in A, and this collection is a set, that is what it guarantees. So, we will see various examples of such property P of x y later. So, we will actually define functions rigorously, then it will be clear what we are talking about in this P of x y. So, there is this final axiom called axiom of infinity, which is the ninth axiom. So, this axiom asserts the existence of an infinite set. So, there exists a set I called an inductive set such that this satisfies these two properties. One is empty set should be there, and whenever x is in I, then you take x union, that singleton x, that is also should be in I. Okay. So, for example, if you start with the empty set inside your I, then the axiom actually implies that empty set union the singleton empty set. So, this is also is supposed to be there in I. Okay. So, now if you think about it, so we can actually consider this empty and then singleton empty, and this becomes element of this capital I, because both empty and singleton empty, they are element of I. And using this, you will be able to actually kind of get recursively like elements that look like natural numbers inside I. And so, we will do that construction when we are doing the construction of natural numbers, but you must have already got an idea what we are talking about. Okay. So, actually this actually completes the set of axioms that I was interested in actually telling about. So, these axioms are called ZF axioms, and they are actually very important in order to define the sets. And later we will see that there is this important axiom called axiom of choice, that is one supposed to actually include among these ZF axioms. Then ZFC will actually give you the axioms for the basic set theory. Okay, I will stop here. We will continue with the basic properties in the next class. Thank you.